All right. Hi, everybody. I think we should get started. So the plan today is to mostly talk about gravity. I'm going to make a significantly shortened homework set that we'll do on Monday. There'll be like 5 problems or so to get you a tiny bit of practice with gravity. It's not up yet. It will be. Yeah, it's mostly gravity today. The only thing that's not gravity today is going to be the very beginning, which is purely for entertainment. Okay? So you have by now heard about pendulums, right? We've talked about pendulums. You're probably sick of them, even though we only talked about them for like 2 lectures. So, what we have here are 2 different pendulums that are a little bit different from what you have seen before. And I brought them here, or asked them to be brought here for entertainment purposes. So, these are both double pendulums, and you won't have to solve anything about them. They will not appear in exams, I can promise you that, and you're about to see why. And if you become a physics major, which I hope many of you do, but I don't know, then you may have to understand them because they're very interesting. So, what is a double pendulum? It's a thing that can go back and forth, but there's like 2 pieces in there. The lower piece can move independently of the upper piece. Seems simple. And if I take them together, and I take it away from the vertical a little bit and let it go, it goes back and forth like a pendulum. However, if I take it pretty high up, and then let it go, at first nothing interesting happens. And then, good luck deriving or even solving the equations for this one. You see what I'm saying? That is psychotic. So this psychotic thing where it can't quite decide just how nasty it wants to get, well, I guess it decided. It's not that nasty. Okay, I didn't crank it hard enough. Okay. At some point, see, so it was okay for a bit, it was kind of just circling, and then it goes nuts. This part where it went nuts, this is called chaotic behavior. So even a very simple thing like this is chaotic. The tolerances are kind of suck. I don't know if you can hear the banging that it hits on the post once in a while. So there you go. That's fine. So I like that one. But then there's another one here that I've never played with before because well, it has a reputation. But I'm gonna do it. So the reputation is this is also a double pendulum, okay? So it's got a stick here, and it's got some swinging circular thing here. And we're basically going to do the same thing, again, for entertainment purposes. The reason I haven't played with this one is, well, it has a reputation for smacking theorists in the face, and I'm a theorist. So I'm going to try hard not to get smacked in the face, but we're going to see, okay? So I'm going to try to crank it and see what it does. You can see that I step back in the interests of, you can see what I mean. If you get too close to it, it will get you. And it's also badly chaotic. I mean, check this crap out. Pardon my language. Like, what is happening, right? You'd think it'd be simple, right? It's just like a dangling thing with another dangling thing hanging off of it. But basically, as soon as you step away from the nice little things we did in this class, it can get interesting. The thing I want to highlight, though, is it only gets interesting if you really crank it. Because check out this thing. It's now settled down, it's going back and forth, just like the pendulum we studied, even though it's much more complicated, and has within itself the capability to do wild stuff, but as long as your motion is gentle, it does the same thing that we know how to understand. So to be clear, if you're an engineer, okay, and you want something like a clock to, like for example, you're building a clock, okay, it's like a grandfather clock that's built off a pendulum. You want it to be doing that. You do not want whatever is happening over there happening inside your grandfather clock and trying to use that to count. So chaotic behavior is usually a deep evil for engineers. You want to stay the hell away from it. Again, pardon my language. But it can happen. It can happen very easily, so you got to understand it. Okay, but in this class, all you need to know is it exists. And you have seen a demonstration of it. You don't have to ever do anything with it ever again. It will not appear in an exam. we don't have to stare at this. Okay, so that was a video in case these demos failed miserably, okay, of the same thing. So, if you want to understand how this works, a little bit more detailed, wait a couple of years, take Physics 4001, that's called Advanced Mechanics, it's not that advanced. After you take Calculus 3, you could do that class, and you'll have fun, okay? But yeah, I hope that someday I get to teach this class, it'd be really fun. That's all I have to say about pendulums and oscillators and all that. So what I want to do from here is talk about gravity. All right. So for that, let me mess with the lights. There we go. The pointer. That works. Yes. Okay. So far in this class, we have talked about gravity as the simple thing where it always points straight down and it gives you an acceleration which is 9.8 meters per second squared. Okay? And it's just proportional to the mass of the object. That was it. Everything falls at the same rate. That's what we said. So today, I want to tell you the actual truth, which is not as simple as that. More precisely, I'll tell you the truth as long as you can ignore more subtle things like called relativity, but it's good enough for most purposes. Okay? So, see, the rules of gravity as we have learned them so far, actually are kind of weird, because like we've talked about how gravity pulls on stuff that's fallen, but every force has an equal and opposite force, right? That's one of Newton's laws. So if I have something fallen, like an apple, the Earth is pulling on it, but that means the apple is pulling on the Earth. Okay? Well, so how does it pull? Like, how does that work in general? So that's the kind of thing that I want to answer today. Okay, so here is the force on an apple. Okay, the A here is the acceleration of the apple. That's why it's written as AA. Of course, we know that that's the acceleration of gravity. This should also be the right formula for the force exerted by the apple on the Earth. In magnitude, the directions are going to be opposite. So let's work out the acceleration of the Earth through the apple. You just manipulate these formulas, and you'll discover that the acceleration of the Earth is equal to the acceleration of the apple times ma over me. Okay, so here's a fun little thing. So the acceleration of the apple, oops, bear with me. Acceleration of the apple is 9.8 meters per second squared. And then, so the acceleration of the Earth is A apple times the mass of the apple divided by the mass of the Earth. That just follows from staring at those formulas and dividing the mass, the force exerted on the Earth by the apple by the mass of the Earth. And so, okay, so the mass of an apple, like 100 grams, so it's like 10 to the minus 1 kilograms. So that's a nice heavy apple. And then the mass of the Earth, I never remember it. It's like 6 times 10 to the 24 kilograms. So the kilograms cancel. The 1/6 is like, leave it as 1/6, and then multiply that by 10 to the minus 25, and that's about what it is. So you can see that yes, the apple's acceleration is 9.8 meters per second, but the whole time the apple is hanging out there and falling down, the Earth is getting accelerated by that much. So but you can see it's this multiplier factor. This is what I'm working out. It's 10 to the minus 25. It's a very small number, so we don't notice it. But how does it work more generally? Okay. So this is something that Newton figured out a few years ago. So Newton realized that gravity is somehow an attractive force between any two masses. And it's directly proportional to both of the masses, and it's inversely proportional to how far apart they are. That's a fancy way of saying the force of gravity follows this rule right here. Okay? So it's the product of the masses of the two objects divided by how far apart they are, squared. And then to get the units right, you need some constant of proportionality, which is called G. That's Newton's gravity constant. I'll write a formula for like what the number is for G in a minute. Okay, if your two objects are planets, so here is the Earth, here is the Moon. I'm not really drawing it to scale, I'm just being rough, just giving you a rough idea. You might wonder, what is the distance between them, right? Is it this distance or something else? Well, the answer is the way you should define it is you should go find the center of the object, go find the center of the other object. They're centers of mass, more technically. And then the distance that you should use in Newton's formula, what letter did I use? Is this one, R. That's how you should define the distance. So if the objects are very far apart, this is not going to matter. But if they're fairly close to each other, it could matter a little bit. Okay. So, and it's always an attractive force, which is to say, this thing is pulled that way, and this thing is pulled that way. Gravity never ever makes anything repel. You may have heard that electric charges might repel with each other. I mean, you haven't been properly introduced to them, but you've probably heard that before. 1302 is going to be all about that. So, electricity and magnetism, electricity can be attractive or repulsive. Gravity is always attractive. That's a weird thing. Okay? Okay. So, well, how is this related to what we've done so far? Okay. So this slide is a little fast. So let me go through it. Okay. So the force of gravity, I can write G, mass of, say, the Earth, times mass of, let's say, a person. So that's the force of gravity between the Earth and a person. Okay? And I forgot to write something about R squared. Okay. So that's the distance between the center of the Earth and the location of the person. So now let's draw a picture. Here's the center of the Earth. And the person, let's say, is a height h above the Earth. Does that make any sense? So now, the distance from here to there is what I want to call little r. So little r is the radius of the Earth plus h. Is that okay so far? So now I want to write this formula again. So G M-E M-P divided by the radius of the Earth plus h, quantity squared, because this is meant to be that. Are you all okay with that so far? So now, imagine h is very small compared to the radius of the Earth. So that is to say, you don't go very high above the Earth. In that case, our Earth plus h is approximately the same as our Earth. That is to say, like, if, what is the radius of the Earth? 6,400 kilometers, I think. So the radius of the Earth. So if you go up 2 meters, to an outstanding approximation, the sum of these two things is still 6,400 kilometers. Of course, it's a bit bigger, but not that much, right? So this is a good approximation. So if that's true, then the force of gravity will be equal to, as an approximation, G, mass of the Earth, divided by the radius of the Earth squared, times the mass of a person. So this is interesting, because this is the situation in which we thought we knew how gravity works before. Because before, in this class, we've been writing the force of gravity is the mass of a person times G. So this implies that this, apparently, See, it gives a formula for g. It relates the acceleration that something feels as it falls to the mass of the Earth and the radius of the Earth. You can go out and measure the radius of the Earth and the mass of the Earth, and you could also find a way to measure g, and you could see what you get for A. And so, here are some numbers that you could use and plug in. So actually, I think it's kind of nice to plug it in and see what we get. Okay. So, according to the formulas I have up there, g is 6.7 times 10 to the minus 11, right? In SI units. The mass of the Earth is 6 times 10 to the 24 kilograms. Okay, that's an SI unit. And then the radius of the Earth is 6,400 kilometers. So that's 6.4 times 10 to the 3, that's kilometers. But I want to get meters, so 10 to the 3. And this should have the right units of meters per second squared. I'm just going to trust that. But let's try to do a quick evaluation. So look, this 6.4 roughly cancels this 6.7. Very roughly. So what else we got? We got, so 10 to the 24 minus 11 minus 9. Oh, there's my problem. This should be squared. Sorry, I went too fast. My apologies. You got to square the whole denominator, right? It's radius of the Earth squared. So let's see what we get. Let me be more careful. Suppose, for the sake of argument, I say that 6.4 squared is the same thing as 6.7 times 6. It's not quite true, but it's not far from being true. Then this cancels with those two. And then I have 24 minus 11 here. And over here I get 10 to the 6 times 2. I don't know what I'm about to get. Let's see. So 10 to the 24 minus 12 minus 11. So this is 12. So this is 10. Holy crap, it worked. Do you see what just happened? We just got that this is 10. Okay, I don't know why I'm so excited about this. But remember, it's 9.8. It's supposed to be 9.8. I just completely cheated and like crossed some crap out and said that obviously I roughly canceling each other. It just worked. If we had worked a tiny bit harder, we would have gotten 9.8. So, the acceleration of gravity on the Earth's surface secretly is that. What good is this? Well, what's good is that now you can figure out what it would be if you go really high up. You can figure out what it would be on the moon, because you plug, the g is the same for everything. You plug in the moon's mass and the moon's radius, you know what the acceleration is on the moon. You could do it on Mars. You can do it on Jupiter, whatever. You can do it anywhere. Shouldn't do it in a black hole. Things get weird. But otherwise, it's okay. There's a hand there. Yes, go ahead. Where do we get the g from? We got to measure it experimentally. We have no chance otherwise. So one way to try to get the g is from astronomical observations. Another way is, let me think. Yeah, I mean, I would say the best way to try to figure that out is from astronomical observations. So you can leave it as a free parameter and then do some stuff we're going to try to explain in a bit and figure out something about orbits. And then you measure stuff about orbits, how long they take, and you can back that out and turn information about g. For the radius of the Earth, that you really can measure by like looking at like what, on a really clear day, how far is the horizon? Like you can use it, get it from that. They ain't interested that much. The mass of the Earth, I think you also have to get from astronomy. Yes?
If we're asking a question like this on the exam versus we're getting like G constant long equations.
So if you get a question of this sort on an exam, you would be given this formula, and maybe an example of the kind of question that might come up. Somebody tells you, imagine you have a planet where the mass of the planet is 3 times the mass of the Earth, but its radius is the same. What's the acceleration of gravity on its surface? You could get it from here, right? Just scale this up, like stuff like that would be fair game, given this formula. So you have to understand like what happened here, but you will rarely be doing this kind of horrible computation that I just did with all these numbers, because that's too much on a short problem, for example. Okay, other questions? There's a question in the back maybe, or was it just stretching? Yes, there's a question here, yes?
So your question like that would have been multiple choice.
That would have been a multiple choice, I just gave an example, yeah. And in case you're wondering, I mean, gravity stuff at the level we're about to do would be like fair game for the final, but like, we're just getting it at the very end. You're only gonna get a short homework on it. It's not gonna be a major focus of the final. The final is intended to be like a broad coverage of the entire semester, so would you be shocked to get a couple of questions on the multiple choice? No. Would you be shocked to get like 3 or something? I would say yes, actually. That would be a bit much. Okay? So, because we have a lot of other things to cover. Other things, other questions? Okay. All right, so it's time to do a chime-in. Slightly ridiculous one. This right here is, believe it or not, a non-Photoshop picture of who is that? A kangaroo. Kangaroo, thank you. Sorry, my English is failing me momentarily. So, the kangaroo is not Photoshopped. The cans of Foster's beer are definitely Photoshopped. Most of you should not have had it yet. Please avoid it, it's disgusting. This particular beer, specifically. Even natural light is better than that one. Anyway, so one of the things, so when I first saw this image, okay, I looked for a funny picture of kangaroos, this came up. They were all really ripped, like this, and I was like, what is happening? So I Googled more pictures of kangaroos, like most of them seem to be surprisingly well built. I don't know why that is. Anyway, the question is, what direction does gravity point in Australia? Your options are up, down, and then ridiculous ones, Australia is a myth for kangaroos don't care, and finally, you can't really answer this question without defining a coordinate system. As you could guess, this is not intended to be a disastrously difficult question. Is it available to you? No, or yes, it is now. So give it a shot, see what you get. Okay, so there are two competing answers, okay, which is down and can't answer without defining a coordinate system. So I can see why people are going with option A. Certainly if you ask Australians which way gravity is pointing, they will tell you down. But from our point of view, if we were antipodally located to Australia, which we're not, but if we were, it would be straight up, right? Australia is on the other side of the world. So basically it means it's kind of ambiguous. And so to the extent there is a right answer here in this very silly question, I think the single best answer is E, and then the next most defensible answer is probably A, and I think kangaroos would care. Yeah, so that one's like that. And Australia definitely exists. Okay. I shouldn't ask if you have any questions, because I don't have much to say there. Okay, I'm going to leave this open. Feel free to change your mind on what you answered if you want. So the next thing is to get a little feeling for how do you use Newton's equation, okay? So let's do that. So I'm going to redraw what do we got here? We got M, a distance L. M, a distance L. Okay, so we got this arrangement. So we want to know which way does gravity point at the center point, right here. Okay? So what we do, the way to answer this question, is to imagine that you take a little test mass with a mass little m, these are all capital M's, stick it at the center and ask which way would it be pulled. That's what we're asking. Okay. So let's start with the easy stuff, okay? So it's pulled up towards this mass by this mass, right? And it's pulled down by that mass. But the force of gravity, remember, is, in general, g m1, m2 over the distance squared. So it only cares about the magnitude of the distance. So the pull this way gets canceled by the pull that way. So there's no force in the y direction. Is that okay? And then for the rest of it, we have no choice but to do a bit of work. So what we're going to do is this thing pulls us that way. So the force along the x direction. There's a force that way, so minus x hat direction. So how big is it? It's g capital M little m divided by L squared plus a force in the positive x direction that way from this mass, g 2m times little m divided by 2L squared. So we can do this out. So we get when we square this, we get 4 downstairs, there's a 2 upstairs. So what you see is that this thing looks like GMM over 2L squared. Sorry, that's getting a little bit too low, but basically this thing is half as big in magnitude as that thing. So basically adding this thing to that thing removes half of this. So we get minus x hat G capital M. And so the force is that way. So you see, gravity goes up with mass, but it goes down with distance, and it goes down with distance quadratically. And so increasing the distance, all things being equal, wins. Okay, any questions about what I just did? Do you see what the idea was? I completely ignored what's happening in the y direction because it's sort of like, if you think about it, clear that nothing happens there. And along the x direction, I just applied the statement that it's an attractive force, added up the forces due to the different objects in the game, and got the answer. Okay. So I said a bunch of stuff here, but it is the same. So the more exciting thing to do with gravity is to talk about satellites and orbits and things like that. So that's where I want to get to. So I think we've all heard that space exists and that we put stuff into space and it's actually useful. The GPS works off of satellites in space. So it's actually an interesting question to ask, how come stuff in space doesn't just fall on the Earth? After all, it's attracted by the Earth, there's a force on it, it's down, how come it's not falling? So that's something we can understand, okay? So for the purposes of what I'm about to say, let's assume that the Earth is very, very, very heavy and we have a very light object orbiting the Earth compared to its mass. Then, to a good approximation, the Earth is just nailed down, it doesn't move, and the thing that's going around it is doing whatever it's doing, okay? So that's a good approximation in practice. Satellites are not that heavy, certainly not compared to the Earth. And so what it's gonna look like is this picture, okay? So we have something that's moving in a circle around the Earth. The Earth is more or less the sum of a sphere, so you go around it, you're going in a circle. And the force of gravity points in toward the center of the Earth. And whatever is orbiting the Earth has some velocity v. So let's try to understand a little bit about how this goes. Okay. So here's the Earth. Here is something orbiting the Earth. Here's how far it is. So it goes around. So let's say it's going around at a speed v. Okay, so now we can ask. The force on this object is just the force of gravity. It's pointing in. So here's the force of gravity. It is g mass of the Earth times mass of the satellite divided by the r squared, where r squared, well, r is the distance from the center of the Earth. So this thing is r. Okay? Now, suppose that the object that's circling the Earth is really undergoing circular motion at constant velocity. Then the force of gravity has to be equal to the centripetal force. Okay, so it's a blast from the past. We've met the centripetal force before, but haven't talked about it for a while. So what does centripetal force look like? It is mv squared over r. You all see that? So which m? Well, it's the mass of the object that's moving in a circle, so that's the satellite. So we set these things equal to each other. So we get g me ms over r squared is equal to m v squared over r. Okay. So now, what can we do with this? Well, we can say the following. It is very hard to orbit the Earth at a distance from the Earth's center, which is less than its radius, right? You cannot have a subterranean orbit, I think. So if that's true, then the absolutely minimum height you could get for an orbit is that of the radius of the Earth itself. Now, in practice, that won't work because the atmosphere is here and there's too much friction and so on. But let's not argue, let's not quibble about factors of 100 kilometers, which is the lowest height for any reasonable satellite. 200 is more common and above. But 200 kilometers is still really small compared to 6,400 kilometers, which is the radius of the Earth. So just for fun, okay? Let's imagine that the satellite is orbiting right at the surface of the Earth. Then this distance is just the radius of the Earth. Then we can solve for v. So how do we do that? So this is the mass of a satellite. That cancels. There's an r squared here and an r here. If we multiply through by r, we get g, mass of the Earth, divided by the radius of the Earth. I just set r to radius of the Earth. That's equal to v squared. So v orbit, the speed in an orbit, is g me over re. Y'all see that? It's just algebra. But this algebra is kind of cool, because this algebra is telling us what tangential speed here you need to be in an orbit. So we can calculate what that is. So if you calculate what that is, I tried to do it. It is not exciting to watch somebody work this algebra at their board, but the answer you will get is about 7,800 meters per second. That is about 17,000 miles an hour. This is why rockets are complicated and interesting and big, because to get something to move in a circle that doesn't end up hitting the surface of the Earth and just goes all the way around, you have to give it an enormous tangential velocity, and that's what the rocket is trying to do. That's almost all of the energy. Going up is the easy part. That's really cheap. That's not enough to get you into orbit. Going up does not mean that you're in space in a practical sense. You're not going to stay there for long. Going sideways is what gets you into space, into an orbit. And you have to go sideways like that fast. It's really fast. And the interesting thing now is we are in a position to ask, how does the speed change depending on how high the orbit is? So you can see, for example, that the higher the orbit, for circular orbit, the higher you make the radius away from the center, the speed actually drops. Kind of interesting. Okay. So satellites have to go around really fast. Now, an example of a satellite that most of us use just about every day, if we ever open our smartphones and use the mapping feature in any way, are called geostationary satellites. These are the ones that send out signals that our phones then use to triangulate our positions and figure out where we are. So if you ever have any kind of location-based service, it's secretly using this kind of satellite, at least when you're outside. Otherwise, it runs off of Wi-Fi. So how does that work? So a geostationary orbit has this weird feature that from the point of view of somebody on Earth, on the ground, the satellite is always in the same point in the sky, no matter what. So how can this possibly work? So you see, the Earth is rotating, and it takes about 24 hours to rotate. So that means that if you have a satellite high enough up that it takes exactly the same amount of time to go around, from the point of view of somebody on Earth, it's just always going to be right overhead. It's going to hover. And suppose the geostationary orbit of interest is circular. Now you can figure out how high up are geostationary satellites, like the Global Positioning System satellites. So let's sort that out. I'll do that on the board to minimize the chances that I go too fast.